recording right now.
Okay.
So as I said, so the presentation part will be 40 minutes today and then around 15 to 20 minutes of questions. So we have the pleasure of welcoming Yongyi Yang, who is a first year PhD student, sorry, at the University of Michigan, working on graph representation learning and the scientific foundations of deep learning. The paper that we will have the pleasure of discovering today is called Transformers from an Optimization Perspective. And so this presentation is one of many presentations that we have scheduled in the future around transformers. So the idea of the reading group would be that any of us who has ideas about people to invite to the reading group, of course, can invite these people. So as I said before on the channel, there is a Google Sheets document on which you can put in the details of a paper or a presenter that you would like to welcome to the group. If you also want to present your own work in the group, it's also very much welcome. So feel free to contribute and propose ideas of people to invite. So right now I leave the floor to Yongyi for his presentation. Thank you very much again, Yongyi, for accepting to present today. And I wish you a great talk. Thank you.
Okay. Thank you very much for the invitation. And yeah, let me share my screen. Okay. Can you see my screen?
Yes, perfect.
Okay, thank you. So yeah, I'm Yongyi Yang from University of Michigan. And yeah, I'm very honored to be here to present my work, Transformer from an Optimization Perspective. This work is published at New York 2022. And also, I am actually like kind of nervous because I don't have much experience like doing a presentation. So please excuse me if I like get confused with my logic or forget what I wanted to say. Yeah, but yeah, I hope I can deliver my message clearly. Okay, so let's get started. Firstly, I want to introduce the idea of this paper, like what we want to do. So as the title suggests, we basically want to explain transformer model from an optimization perspective. And the idea is that, so normally we know that the training of a deep learning model is an optimization, right? So the idea is we want to also model the forward process also as an optimization process. So which the framework can be written in this way. So for training, we are optimizing the loss function and find an optimal like model parameter W. And for the forward process or for the model, we want to view the each forward layer as an optimization step of a certain function which we call energy. Yeah, but there's not a specific meaning why we call it energy, but just let's call this objective in the model as energy. So yeah, it can be shown like this. So when we're doing the forward process of the model, we want to find an objective function which we call energy function, which is descending along the forward process. So which means we want to find an objective function, and the optimization are exactly the forward layers of the model. So as a kickstart, I want to show a simple case where we can we show how to like recover a feed-forward network from projected gradient descent. So I guess you should be familiar with projected gradient descent if you have taken any like optimization courses or machine learning courses. So yeah, but anyway, so basically consider this. Consider if we have a matrix W bar which is PSD, and we have this objective function and this constraint we want to optimize y, where y is actually the corresponds to our hidden representation in the deep learning model. And so this is basically a convex optimization with a convex constraint. And we know that if there's a convex optimization problem, we can, if it is without constraint, then we can optimize it with gradient descent or subgradient descent. Yeah, but there's a convex constraint, and for convex constraint, we can actually add another projection step. Like at every step, we first do an unconstrained gradient descent, and then project the representation we get to the set that we want this variable to be. And there are theories shows this process will converge to the optimal point of this problem. And this say is the constraint here. Basically, if we constrain, basically this say is the space that all entries of the vector is greater than 0, is like non-negative. So we can do a projected gradient descent like this. And yeah, this is very like simple. But if we so look at these equations, if we set the alpha to be 1, and notice that this projection to the set C is exactly the ReLU activation function what we use every day. So, and if we set alpha to 1, then the whole updated rule can be written as this. And that is exactly the FFN. So in this way, basically we recovered that FFN from the projected gradient descent with this energy function. So that's the whole idea. And but yeah, FFN is a very simple model, and this problem is also very simple. So why that is? Sorry. Yeah. So why that? Anyway. So we want to explore that if we can also apply this framework to explain transformer as an optimization problem or as an optimization process, or specifically the transformer encoder. So this is the figure of transformer encoder, and there are several major obstacles. Actually, there are 2 major obstacles. The first is there is a self-attention block, and the self-attention is like very different from feed-forward structures. So like in feed-forward structures, we basically in each step we are like multiplying the hidden representation with some matrix W here. But in the attention, we are also multiplying this Y. Say this Y is the hidden representation by some matrix, but this matrix is not a constant. It's dependent on the Y. So that is kind of like difficult to handle with. And the second problem is that there are 2 different processes in transformer encoder, basically the self-attention and the feed-forward network, and they go alternatively. So it's kind of difficult to unify them into a single optimization objective. Yeah. And actually, we cannot expect this process to converge to a stationary point. And I will explain why later. And yeah, so let's solve these problems one by one. So we will consider the first problem at first. So as I mentioned, there is a self-tension. And so the problem becomes, can we find an energy function such that this self-tension we return in this form that we ignore the multi-head for now, which is not like very essential for transformers. Yeah, so we want to show that can we find an energy function such that this self-attention is a descent step of that energy, and we will show that. Before diving into the details, I want to first mention about the logic of this paper. Like if you want to read this paper afterwards, and it might be helpful to you. So basically, rather than thinking of a specific problem at first, what I prefer is to firstly study an abstract problem, and then like like at first we don't design it with the physical meaning. We will firstly look at an abstract problem, which like everything is defined in like mathematics. And so basically in this equation, we have all the variables have their physical meanings. The y, the hidden representation, the q and k are the like are the model parameters. The wa is also model parameter. Let's forget about that. Let's just consider them as variables. And we will first study the general case and then aligning it with physical meanings afterwards. Okay. So now we want to show you how to recover the self-attention from the optimization perspective. But at first, I want to introduce a little bit of non-convex optimization, which I don't know if all of you are familiar with that, but so like in case anyone is not familiar with that, I will first introduce it a little bit. So modulation minimization is a principle in non-convex optimization. So basically, it is like if we want to optimize the function fx, which might be like whose property might be very bad. Maybe it might be like non-convex or non-smooth or even non-continuous. And if we want to optimize the fx, and one technique we can use is that at each point x0, we construct an upper bound of fx, which is equal to fx at the point x0. So g x0 is equal to fx0. And if we can optimize g, and we can guarantee that the x1, like say x1 is the descending point of g function, and then it will also descend f. So yeah, so in this principle, we can basically at each step we can replace our target function f with the upper bound of it, and update the upper bound. And the upper bound g can have like whatever property we want. It can be smooth, it can be convex, and it can be very simple, which is easy to optimize. Yeah, but how to find the specific form of g is depend on the specific problem. So that's why I call it an optimization principle instead of an algorithm, because we need to know the specific scenario to find the specific form of g function. Yeah, and so let's consider this energy function. So basically the summation over every pair of I and j, and the rho function applied to the distance over y and yj, and y and yj are our, so this y and yj is just this y, the rows of this y. Consider this problem where this rho is continuous, non-degrading, and concave. And because rho is continuous, non-degrading, and concave, so basically it is like, as I said, it's a non-convex function. So directly using like gradient descent might not converge to the optimal point. So we can use the marginalization minimization principle in this case. And because rho is like has this property, we can show that a linear function or a phi function is always an upper bound of g. So it is shown in this figure. So consider this is the rho function, and at each point x0, we can always find an phi function, basically a line, which is an upper bound and is like equals to rho at this point. So which means at each iteration step, we can change the rho function to an phi function, which basically is kx plus b. But we actually don't need b here because the best term is like irrelevant to the optimization variable. So basically it does not change the optimization problem. So we only keep k here. So basically at each step we can replace this rho function to a coefficient k, where this k is like depend on our point here. This k is basically the differentiate of rho function at our current point, at current point. And consider this specific function, like rho z is minus exponential minus z. And do some calculation, basically do some calculation. And we will find the specific form of this coefficient k, which is like this. And if we do a normalization of it, it will become this. And we will find this is exactly like our favorite inner product self-attention with softmax normalization. Yeah. So from this principle, with this specific rho function, we find that we can actually, so basically it means if we are optimizing this energy function with this specific value of rho function, the descending step can be exactly the softmax. Yeah, so let's return it in the matrix form. It will look like this, but it is like still kind of different from what we want, because let's recall what we want. What we want is there should be some parameter in there basically should be a F transformation inside the softmax, which is a model parameter to be trained. So but what we got is there's no parameters inside the softmax. We can do that by a simple representation trick. So basically, if we reprioritize our y to be z times w, and w is invertible, and then we can show that the optimization of d can be a softmax where there's a parameter matrix inside this softmax. So in this way, we basically derived a way to explain the self-attention in the optimization unfolding perspective. And remember, our next problem is that can we, like, let's say we have two different components, the feed-forward structure and the multi-head attention, and it's likely that these two components will not like converge to a stationary point. So, sorry. Yeah. So we want to somehow like find a unified energy for them, but it's likely that they will not even converge. And here I will like explain why we don't expect them to converge. It is because for the feed-forward network, I have shown in the first that it can be written as this, as the unfolding of this optimization problem. And for the self-attention, we have just derived an optimization problem in this way. And so basically, which means these two components are optimizing two different energy functions. And nobody can guarantee that these two energy functions have the same stationary point. So we don't know. So it's likely they will not converge to the stationary point. Like even if in each optimization step we optimize to the optimal point of the corresponding energy function, then they will still like oscillate between these two different optimal functions, which means it will not converge. So we must do a relaxation of the problem. So consider what if we don't require the process to converge to the stationary point, but rather we just wanted to converge to a neighborhood around the stationary point, to a stationary point of some energy function. So that's our thought. And so why we can why we can consider this? So basically, the idea is that let me show you this way. So basically, consider a general case. Like consider we have two objective functions f and g, and we are alternatively optimizing f and g, and we want to show that the optimization process can converge to a neighborhood of their summation h. H is equal to f plus g, and why that's possible. The idea is that consider if the y infinitely far from the optimal point of H, then these three optimal points, basically the optimal points of H, optimal points of F, and optimal points of G, will be like nearly in the same direction. So which means whatever optimal point you are like you are like nearly optimizing another function. So when y is like infinitely far away. So this figure shows this case. So basically, when y is, so consider this is the starting point of y. When y is very far from the optimum point of h, and we are alternatively optimizing f and g, it will like kind of oscillate, but it will still like become closer and closer to h. But when it becomes close enough to h, it will like oscillate around it and will not converge. So we want to show that if y is sufficiently far away from the global optimum points of the two energy functions, then if we alternatively optimizing the two different functions, then it can be viewed as optimizing the h function. So we want to give a condition that so the question is how far away can y be? So we want to give a condition that we can guarantee the descent of h, and we derived this condition in the paper. So basically, it will depend on the convexity of h, the Lipschitz constant, and another constant which is depend on the this alpha are the step sizes and the Lipschitz constant of f and g, and this will this basically characterize something called an Apollonian circle, which is shown as a blue circle here. So basically, consider if this is the optimum point of f and this is the optimum point of h, then the area characterized by this inequality will be one of the blue circles, which is shown in this figure. So basically, it shows that if this right hand side of this inequality is sufficiently large, then we can guarantee descent of h in almost the whole space except the small circle around yh star, which is the optimal point of h. And this circle is actually goes to zero if alpha is like sufficiently small. So yeah, so this is how we want to handle this alternatively optimizing problem. So yeah, so basically this is a general case, like, and we can apply our problem in like we can basically apply these two different objective functions into this general framework, like substituting f and g to be this function and this function, and we can get a result for transformers. Okay. So another problem is that, so basically in these problems we didn't consider like, so basically in this problem we are just doing two like gradient descents, and we didn't consider the ReLU activation. But as we said, if we want ReLU activation in the FFN, we need a constraint of x inside some area, some like a specific set, and do a projection into that set. So in an even more general case, we are not only alternatively optimizing f and g, but also have a projection onto a space, especially the ReLU function, and that is more complicated. And for the time limitation, because of the time limitation, I will like ignore this. But the idea is similar. Basically, we want to show that under specific condition, that y is sufficiently far away from h, then we can show the descent. So that's a basic idea of this paper. And there are still some time left, so I want to also discuss some possible extensions and limitations of this paper. So one extension is that, so as I said before, the technique we use to like derive ReLU function is to view ReLU as a projection onto a specific set. And so one problem is that can we generalize it to other activation functions, because other activation functions are not all projection operators. And so, and the way that the projection operator can be viewed as a special case of so-called proximity operators. And if you have taken some like optimization courses or convex analysis courses, you might be familiar with this proximity operator. So basically, the ReLU function can be written as this. So every function can be written as this form is a proximity operator of this phi function, which this phi is the penalty term of z. And for ReLU, this phi function has a like specific value. And for the projected gradient descent, yeah, there's also a generalized version of proximal gradient descent. So basically, in each step, you do a gradient descent and then do a proximity operator on the representation, and then it will still guarantee converge. So, so as long as we can write the nonlinearity as a proximity operator, then we can involve them in this framework. So the problem becomes that what functions can be written as proximity operators, or can other activation functions we use be written as proximity operators? And I give a reference. This paper basically shows sufficient and yeah, the condition of sufficient and necessary condition of a function that being a proximity operator. So basically, there are two conditions. The first condition is that this operator can be written as a subgradient of a convex function, and the second condition is that the operator is non-expansive. However, the second condition is actually not necessary. It is necessary for the proximal function to this proximal problem be convex. But if we don't need this convexity, then we don't need the non-expansiveness. So the only necessary condition is that the operator can be written as the subgradient of a convex function. And actually, any continuous and non-decreasing function can be written as this. So many functions we use, like softmax, tanh, and like ReLU, leaky ReLU, can be written as proximity operators. So they can all be involved in this framework. And there's also a limitation in this work, which is the symmetry of model parameters. So basically, in my presentation, you might have noticed that we are always assuming that the model parameter W to be like PSD. So basically, this is in the self-attention, where this W is this parameter W is like constructed by this WW transpose, which is necessarily PSD. And in the derivation of FFN, we also assume W be PSD. So actually this PSD condition can be relaxed to symmetric, but we cannot further relax it to asymmetric. So that's I think that's a major limitation of this work. And actually, all of this kind of works, this kind of optimization unfolding works, they basically all have this problem. And there are some possible ways to avoid this problem. One way we'll consider that is that we might be able to illustrate that symmetric and asymmetric weights have the same capacity, like after nonlinear activations. And there's a work in this work basically have like explored like the capacity of symmetric and asymmetric weights, and basically this paper proved that the symmetric and the asymmetric weights have the same capacity, and almost all like this kind of optimization of unfolding papers will cite this work to show that to like solve this issue. However, after carefully checking this paper, I found that the conclusion of this paper is actually false. So like if you are interested in this, you can check the papers and see why it is false and why it is actually cannot be applied to most of the cases. So actually, it is still an open problem that if we can, if the symmetric and asymmetric weights can have the same capacity, like after maybe a specific nonlinear activation. So that is one possible direction. And although this paper exists, it is like not enough for illustrating our purpose. So it is actually still an open problem. And there's another possible direction is that if we only unfold the optimization for finite steps, then we can use a trick that we can construct a very large weight matrix like this, and we initialize our y to be y0 and a lot of zeros. And then if we only do like finite steps, then we can each time this y will like shift to the right by one step, and will be applied to an asymmetric transformation. So if we unfold it to like d steps, or maybe k, that should be k here, to k steps, then it will be applied to k asymmetric transformations. And you can also use nonlinearities on this, like add ReLU on this. It will also be okay, but this only works for, yeah, this solution also is also mentioned in many this kind of works, but still this is kind of weird because firstly, it will only allow you to unfold like finite number of steps. Also, it will construct a very large like model parameter, which is kind of weird. So yeah, so the symmetrical model parameters, I think is still a direction to explore. And if you want to explore this function, if you want to explore this direction, you can consider these two directions or other ideas. And if you want to discuss with me, you can like just send me an email to discuss me with any ideas you have to solve this issue. Okay, so there's another extension is that layer norm. So remember, at first we said we ignore the layer norm and the residual connection for now. And yeah, for the residual connections, basically you just need to what do I say? So for residual connection, it's kind of easy. You just need to choose a step size of alpha instead of 1. Another is like less than 1. Then you can get residual connection. And for layer norm, so basically you can decompose the normalization into two processes, like translation and rescaling. And it turns out that both these two transformations can be written as the descent step of a specific energy function. So it can also be involved in our framework. So that's how we can deal with layer norms. And yeah, basically that's all. So thanks for listening. And if you have any problems, I'm happy to answer them.
Thank you very much for this very exciting presentation. I guess now the floor is open for people to ask questions, and I will stop the recording.